Alright, so in this video I'm going to be explaining another important article about domain adaptation. But this time we are talking about domain generalization, so our target is unseen. So the title of this paper is Learning to Balance Specificity and Invariance for in-domain and out-of-domain generalization. For domain generalization, the goal is to learn from a set of source domains to produce a single model that will best generalize to an unseen target domain. As such, many prior approaches focus on learning representation which persist across all source domains, with the assumption that these domain-agnostic representations would generalize well. However, often individual domains contain characteristics which are unique, and when leveraged can significantly aid in domain recognition performance. As I said, if this is a feature vector, the first block could be feature invariant, domain invariant features, and the rest of that is domain specific. In domain generalization, we don't ignore these domain specific because they are unique. When leverage can significantly aid in domain recognition. So when we introduce domain specific masks for generalization, a model for improving both in-domain and out-of-domain generalization performance. To produce a model which best generalizes to both seen and unseen domains, we propose learning domain-specific masks. The masks are encouraged to learn a balance of domain-invariant and domain-specific features, thus enabling a model which can benefit from the predictive power of specialized features while retaining the universal applicability of domain-invariant features. We demonstrate competitive performance compared to naive baselines and state-of-the-art methods on both PACS and DomainNet. So at training time, we optimize for a combination of domain-specific and domain-invariant learned representations. Partially invariant representations are indicated as color combination blue-yellow, which is green. At test time, these learned representations that capture a balance of domain specificity and invariance allow the classifier to make a better prediction for given test instance while leveraging domain-specific features from the most similar source domains. So they also have this interesting partially domain-invariant component, which I haven't seen in any other article. Usually people talk about domain-invariant and domain-specific, but this paper is interesting, is also talking about partially domain-invariant components. And you see that we introduce domain-specific activation masks for learning a balance between domain-specific and domain-agnostic features. Our training, which on the left you see the pipeline on the left here. Our training involves incorporating domain-specific mask in the vanilla aggregate training process. In the middle, for an image belonging to a sketch, we sample a binary mask from corresponding mask parameters, which is then applied to the neurons of the task network. And finally, on the right, you see post-feature extraction. An element-wise product of the obtained binary mask is performed with the neurons of the task layer L to obtain effective activations being passed to the next layer. The mask and network parameters are learned end-to-end based on the standard cross-entropy coupled with SIOU laws penalizing mask overlapping among the source domains. So these are mask activations are forwarded from layer L to L plus 1. And you see these are binary masks sampled from soft distributions. But the blue one is the neurons. So you know what is domain generalization? The unseen, we have unseen targets, or some people call unknown targets. And we have multiple sources. So our goal is to learn representation which capture a balance of domain-specific components and domain-invariant components, capturing information containing multiple source distribution in such a manner allows us to make better predictions by automatically relying more on characteristics of a specific source domain in situations where an instance observed at test time is relatively similar to one of the sources. So given k neurons at some layer, we introduce parameters for each of the source distribution. During training, for instances, for some domain D, we first form these mask probabilities. We use sigmoid operation for them. And, because they are binary mass, either 0 or 1. So they are sampled from a Bernoulli distribution. I've also seen mixture of Bernoulli distribution in a paper about graph generation, that in the final decision making, they used mixtures of Bernoulli. So it's very common to use this distribution. Upon sampling masks for individual neurons, the effective activation which are passed on the next layer, an element-wise product of obtained activation and a sample binary mask. During training, we sample such binary masks corresponding to source domain of input instance, thereby making feed-forward predictions by only using domain-specific masks. Under this setup, the prediction made by the entire network can be expressed as this, where this M sub I denotes for domain D, denotes sample mask for domain D, being applied to all neurons in the task network. We learn the mask parameters in addition to parameters of network during training. However, note that mask parameters, they cannot be updated during directly using backpropagation, as the sample binary mask is discrete. So we approximate the gradient through sample discrete mask using straight through estimator. We use a discretized M sub I sub D during a forward pass, but use the continuous version of this mask during backward pass by just approximating it. Even though the hard sampling step is non-differentiable, gradients with respect to M sub I serve as a noisy estimator of the gradient. Now we want to incentivize domain specificity. To ensure the mask capture neurons that are specific to individual source domains, we need to encourage specificity in the mask while maximizing predictive performance on the source set of distributions. To incentivize domain specificity, we introduce an additional soft overlap loss that ensures masks associated with each of the source distributions overlap minimally. To quantify overlap, we compute the Jacquard similarity coefficient, also known as IOU, among pairs of source domain masks. However, as IOU is non-differentiable, it is not possible to directly optimize for the same using gradient descent. Therefore, inspired by prior work in reference 40, we minimize the following soft overlap loss for every pair of source domain mask because this domain could be 3, this domain could be 5. For every pair we do this. So this one, this one is approximate, this dot product approximate the intersection, but this one is different from that dot product. This one is the element-wise product, and K denotes the number of neurons. So during the training, SIOU ensures predictions for instances from different source domains are made using different subnetworks. To summarize, for a set of source domain D sub S, the overall objective we optimize during training ensures two things. First, good predictive performance on discriminative tasks. Second, minimal overlap among source domain masks. So figure 2 summarizes our training pipeline. To obtain a prediction at test time, we follow soft scaling scheme similar to dropout paper. Recall that sampling from domain-specific softmax essentially amounts to sampling a themed subnetwork from the original task network. However, since it is intractable to obtain predictions from all possible, there are exponential number of possibilities, possible domain-specific subnetworks, we follow a simple averaging scheme that ensures that the expected output under the distribution induced by the mask is the same as the actual output at test time. So we show how optimizing for SIOU leads to masks which are specialized for the individual source domains.